Hey Tom, do you run into a lot of questions about the NEC code?
Well, Dan, Article 250, grounding and bonding, that's a big area where there's a lot of confusion, and you'll get a lot of debates even at the code panels amongst engineers and installers on all the different terms that we have to use and getting everything the same and everything right. It's a target-rich environment for questions.
Rick, how about for electricians? I mean, is it really pretty straightforward, or do they kind of know what they're doing?
We run into a lot of confusion about grounding and bonding as far as transformers, bonding XO, when to bond, where to bond, with the different starts and stops of service, earth ground, building steel, foundation grounds. There's a lot of confusion based on that.
I mean, I see it with power quality. It's like, if it's 3-wire, 4-wire transfer switches, all this kind of stuff, even coming down the pole, going into the resi room here, where do we ground it, where do we bond it? I mean, at the end of the day, if a power quality person says they don't understand a problem, a lot of times, or if they act like they understand the problem, but they really don't, they might say, oh, it's grounding related, and they kind of just move on. That's a problem for me.
It's very confusing as an electrician to take the theory and apply it into the actual applications. So the more hands-on you can get with it, the better we can all become as installers and engineers, and more problems will get solved ahead of time instead of after the fact.
There's a lot of theory there. Getting your hands on equipment in facilities that provide that ability in an electrically safe, controlled environment, that's the key. That's where the rubber meets the road, actually seeing the fittings, seeing the bonding, and all of the meeting the National Electrical Code and practical application of grounding and bonding. It can't be replaced.
I agree.
Why are we talking about this? Why do we worry about grounding and bonding? We're worried about, and we want to establish an effective ground fault path, and we also want to think about those touch potentials or step potentials for two different reasons. First, the effective ground fault current path, we're intentionally constructing a low impedance conductive path that's designed to carry the fault current from the point of where the ground fault occurs in the system back to the source. And the reason we do that is we want to make sure that we open the overcurrent protective devices, which could be equipped with ground fault protection of equipment or GFCI protection. We want to make sure that we open those and give enough current for those to detect that fault. Now, you want that impedance to be as low as possible because we want to drive the fault current as high as possible. We have to understand the basic principles of ground fault currents will flow anywhere they can get a chance to. We're not going to guarantee that only the fault currents will flow through the equipment grounding conductor. And that's why we can't make the mistake of thinking that this grounding and this bonding will prevent someone from the electrical hazards of shock. When we talk about those electrical hazards of shock, we want to reduce our touch potentials or our step potentials. We want to keep everything at the same potential and be like that bird on a wire. So we expand this concept. If you think about the concept of touch potentials or step potentials and keeping things at the same potential, you can think about this in regard to substations, where we establish that grounding grid underneath the substation, or around swimming pools, where we're doing equipotential bonding. This will reduce the likelihood of voltage potentials, and we understand that a potential difference between two voltages is what's going to drive current. So if we can reduce or eliminate that potential difference, we can reduce the likelihood of shock, so we can reduce the likelihood of damage to electrical equipment.
With respect to grounding, transformers are often an area of concern and discussion regarding when, where, how, and why to ground the transformer. This is a simple single-phase example of a transformer like a 480 to 120 volt control power transformer. Considering the secondary windings, one of the two legs, typically X2, would be connected to ground. This would allow you to establish a reference to a known reference on the secondary of the transformer when this is required for safety, power quality, or by NEC requirements. X2 is also considered the neutral conductor for typical low voltage applications and would only be grounded at the transformer and at no other point downstream on the circuit fed from the transformer. For this situation, a simple wire connecting X2 to the incoming ground wire coming from the primary of the transformer would suffice for a control power transformer. This ground would also be bonded to the transformer case to ensure that the case and all metal parts remain at a constant potential for reference to the known ground conductor. I've seen many instances where this ground connection was not done to supposedly make it better for power quality reasons, but yet it almost always made it worse without the ground connection, and electrical equipment was damaged. Why do we only connect ground once? Well, if we incorrectly ground the neutral downstream of the first connection, here's the problem. Load current will return on both the neutral and the ground conductor, which is connected to all the metal parts in the system. For that reason, current will divide at the subsequent neutral to ground bond, and load current will flow in the ground. We absolutely don't want current to flow in the ground conductors unless there's a ground fault. Having a single neutral to ground connection ensures that this will be the case. In this next section, we will explain how this applies to larger three-phase transformers.
Let's start with the simple definitions that we find in the National Electrical Code, or the NEC. And we're going to focus on Article 100, where most of the definitions are spelled out for us. Terminology is really important when we're communicating around grounding and bonding. So these definitions are going to be important so we're all speaking the same language. And what we're going to do is we're going to start with the term ground. The National Electrical Code tells us that ground is the earth. I think it's the shortest definition in the National Electrical Code. We define ground as the earth. So anywhere where you use the word ground, you're thinking you're tying to or you're connecting to the earth. Because the earth does not come with terminals, we have to establish a connection to earth, and we do that through what we call the grounding electrode. So a grounding electrode is a conducting object used to make a direct electrical connection to the earth. This is typically your ground rod, very common solution with regard to your grounding electrode. It could be your grounding grid, it could be the U for ground, or inside of a building it could be the structural steel, the water pipe coming into your home. Those are all grounding electrodes. And you could have multiple grounding electrodes at any one installation. And what the National Electrical Code tells us is that we need to connect all of those grounding electrodes together, and we create what the NEC calls the grounding electrode system. The grounding electrode system is when we pull all of those grounding electrodes together. So every grounding electrode that we have on that site, whether it be the U for ground, the water pipe, or other means that are identified in the National Electrical Code, we have to pull all of those together as a system. And that we call the grounding electrode system. Now let's talk about the grounding electrode conductor. This is the conductor used to connect the system neutral conductor or grounded phase conductor or the equipment to the grounding electrode system. Grounded, when we use the term grounded, this is when we say we are connected to the earth or to some body that extends that earth connection. Ungrounded is just the opposite, right? It's not connected to ground or to a conductive body that extends that ground connection. All right, so now we're going to talk about the grounded conductor. Now, this is the system or circuit conductor that is intentionally connected to the earth at that one point. We usually refer to this as the neutral. And its ugly brother, the ungrounded conductor, a circuit conductor that is not intentionally connected to the earth. So this is usually your phase conductors. Your grounding conductor. I know we're saying a lot of terms here with grounded conductor, ungrounded conductor. Now we're going to talk the grounding conductor. That's a conductor that is used to connect the equipment or the grounded circuit of a wiring system to a grounding electrode or to the grounding electrode system. Now, bonding and jumpers. So we're going to get into an area where we're pulling things together now. We're talking about bonding, and what the National Electrical Code defines bonded as connected to establish electrical continuity and conductivity. This is a very important term as we work throughout the power distribution system. Bonding conductors, or what we call jumpers. These are your reliable conductors to ensure the required electrical conductivity between metal parts required to be electrically connected together. Your service equipment, so when we get into service equipment, this is where your utility is connecting into the power distribution system. And in this equipment is where we're going to define some very important bonding jumpers. One of those is the main bonding jumper. The connection between the grounded circuit conductor and the equipment grounding conductor, or the supply side bonding jumper, or both at the service. So this is your main bonding jumper, that point where we pull both of those conductors or those systems together. Now your supply side bonding jumper, this is the conductor that's installed on the supply side of the service or within the service equipment enclosures, or for a separately derived system that ensures the required electrical conductivity between the metal parts that are all required to be electrically connected. Now we're going to move over to transformers for grounding and bonding inside of transformers. When we move into a transformer, we're talking more like in a separately derived system. This is your electrical source or other than a service having no direct connections to circuit conductors of any other electrical source other than those established by grounding and bonding connections. That's your separately derived source. So let's talk about that transformer. If I have a very common transformer you'll have in a power distribution system is your delta Y grounded transformer. There is an isolation between the primary and the secondary. You're establishing a separately derived system on the secondary of that transformer. And if we look over at a generator, you'll typically see people drive a ground rod next to a generator. And they'll bond the enclosure of that generator with that ground rod. If they connect the neutral to that enclosure inside the generator, they're establishing a separately derived system. Now, why is that important to understand that action will create a separately derived system? Because it will drive what you do in the transfer switch. If you bond that neutral to ground in the generator and you establish a separately derived system, you're going to need to switch the neutral in the transfer switch. And that would mean that you would need a 4-pole transfer switch instead of a 3-pole transfer switch. And if you're bonded in the generator and you're not switching the neutral, you have two separate areas where that neutral conductor is being bonded and you could have circulating currents. You could cause GFCIs or ground fault protection of equipment not to work and function correctly. A simple fix, if you didn't buy the right transfer switch, 3-pole transfer switch, and you bonded that neutral in the generator, is to just lift the bond in the generator. Your generator instructions will tell you how to do that. Now, we've established what a separately derived system is. And we know that depending upon, especially in the case of a generator, depending upon how you bond things in the generator and you establish a separately derived system, that will drive the solutions that you purchase and install. A non-separately derived system, good examples of those are your downstream panel boards or that generator that doesn't have an established neutral ground bond in there where you're using the 3-wire or a 3-pole transfer switch. Those are your non-separately derived system. You're keeping things separate. You're keeping your grounded conductor separate from your equipment grounding conductors in all of those locations. All right, so let's talk about the system bonding jumper. This is the connection between the grounded circuit and the supply side bonding jumper. So we have a grounded circuit conductor out there. We have a system ground where we're establishing our ground, and we're going to need to bond those two together, and that's what this is all about. Your equipment bonding jumpers, these are your connections between two or more portions of the equipment grounding conductors. We have to make sure that we bond everything together, and anytime we put jumpers in between your equipment grounding conductor and any of the steel that needs to be bonded, those are your bonding jumpers. Equipment grounding conductor. So we've used that term, let's define it. The equipment grounding conductor is the conductive path that is part of an effective ground fault current path and connects metal parts of the equipment to the system neutral or grounded phase conductor. And that's done back in one location. Think of this as that bare copper conductor that you carry out to all of those loads. Or if you open up any receptacle, you'll see that bare copper conductor that's in the receptacle outlet. That is your equipment grounding conductor. We want that to be a low impedance, and we want that to carry fault current should a fault occur, a ground fault occur in the system. All right, so everything that we've talked about so far has been about grounding and bonding of components and electrical systems. We're We're establishing that connection at the service or at our separately derived system between the grounded conductor and our equipment, bonding and ground and earth. Now we're going to talk about system grounding, and we're going to hit solidly grounded systems versus resistance or impedance grounded systems. Solidly grounded, when we use that type of terminology or that type of a system, we have a solid connection to the earth at some point in the power distribution system. There's no resistor or impedance inserted in that connection point. Ungrounded systems are just that. There's no connection to ground or a conductive body that extends that ground connection. We're insulated from ground. Your impedance or resistive grounded systems. These are systems that are connected to the ground, to the earth, through an impedance. All right, last statement about grounding, objectionable currents. Now, we use this term objectionable currents in Article 250 of the National Electrical Code, but you know, there's no definition in the NEC. And when there's no definition, you know what you do? You make it up. So this is my definition. Current flowing on the effective ground fault current path during a non-faulted condition. And I think to best understand this, let's just talk about an example that you are probably well aware of because it received a lot of attention over at least the last 2 cycles in the National Electrical Code. And these are those motion sensor switches, type switches, that you'll find in either residential homes or commercial buildings, where you walk into a room and it turns the light on. If you think about how we wired residential homes or any types of structures when we came down to a light switch, what did we do? We brought one set of conductors, and that was our hot conductor. And we bought an equipment grounding conductor as well. And we did not bring a neutral. When we had a standard light switch, that was perfectly fine because we're just breaking one conductor. But when you install a product like a motion sensor switch, which needs to have power, so you need a neutral conductor to provide the potential voltage to power up electronics. If I opened up a light switch and I don't have that neutral conductor there, I could get that power by taking hot to ground, the equipment grounding conductor, to power up that unit, and it will work. But it would put current over the equipment grounding conductor. And based upon the definition that we just created and just talked about, that would be current flowing on the equipment grounding conductor that's not because of a faulted condition. That would be what we call objectionable current. And that is not permitted by the National Electrical Code. So changes have occurred over the last few cycles, 1, to prohibit the use of those products, and 2, to require the pulling of a neutral at those switch locations. So in case you installed a technology that required to be powered up, you're not likely to grab that equipment grounding conductor to get that done. You will properly use the neutral grounded conductor to get that done. So hopefully that helps you understand what we mean by objectionable currents. And remember, all of these terms that we just talked about, it's critical that we use these terms correctly as we communicate to make sure that we all understand each other and we get things right. And hopefully this little review helped you. For a larger electrical system, we have to consider many other things to properly ground and bond this electrical system. We will give a few examples of components and systems to hopefully clarify any confusion that may arise. Let's talk about 2 important terms, service entrance and separately derived systems. Simply put, think of service entrance as the electrical equipment fed from the utility source. This may include a transformer, a service disconnect, or other protective devices. There are very specific rules in the National Electrical Code for service entrance equipment and grounding. Think of a separately derived system as a point downstream of the service entrance equipment where electrical isolation creates a new source. Usually, this is a new transformer connection or perhaps a generator. In either case, a new grounding and bonding scheme is required for this separately derived system. Here's an example of a separately derived system with delta Y 3-phase transformers. Here is the grounding electrode conductor, and the main bonding jumper. This establishes the grounded conductor that we talked about in the previous section. Let's show you how a residential service and a load center are typically grounded and bonded. A residential system is a solidly grounded system with two HOTS and a grounded neutral conductor, which is a single wire. This allows the utility to ground the transformer and you to ground your main load center without dividing the current going back to the source because there's only one wire. NEC section 250.20b tells us that all premises wiring systems shall be grounded when the voltage to ground on the ungrounded conductors doesn't exceed 150 volts. So now let's look at a commercial power distribution system. As you get outside the residential world, you have more options based upon the applications. For example, data centers and other systems that demand a higher service continuity may opt to use high resistance grounded systems as opposed to solidly grounded systems. Many commercial and light industrial systems will be solidly grounded. Let's show you how a pad mounted transformer might be grounded and bonded, and how the indoor switchboard might be grounded and bonded for a solidly grounded commercial power distribution system. Finally, for larger systems using unit substations and switchgear, here's how the grounding and bonding is done for those systems. For larger systems like the pad-mounted transformer or the switchgear, if the utility owns the transformer, we would see the neutral to ground bonding jumper installed inside our switchboard or switchgear, and we would bring the grounding electrode conductor into that service equipment. That is why it is clearly marked as service entrance equipment or suitable for use as service entrance equipment because it has the capability to bond the neutral to conductors inside that equipment. The transformer is a very important piece of a power system puzzle because it establishes the voltage levels and that neutral point on the power distribution system. Depending upon the winding type, the transformer establishes the configuration that you will have to use. For example, the transformer connection may be a typical one like the delta Y, or maybe more unusual like a delta zigzag or a high leg delta. Well-established methods for grounding and bonding these transformers can be found in our consulting application guide. Now, everything that we have just discussed around power system grounding is separate from the bonding discussion that we had because regardless of the grounding method for the power distribution system, the equipment grounding doesn't change and bonding is still critical and required. The difference is that the grounded conductor and the grounding conductor must be insulated from each other outside of one point in the power distribution system where they're bonded. Any subpanel in a power system must not have a connection from the grounded conductor, which is typically the neutral, to ground. Remember too, this is only relevant if you have a grounded conductor because with a delta high resistance system or an ungrounded system, you're not going to have that grounded conductor.
Power quality considerations are important as you consider when, where, how, and why to ground your power system. The key is to focus on things that can be controlled and solved. The main power quality concerns that are usually the focus of grounding studies include lack of proper grounding. Beyond the safety concerns, equipment can and will fail with improper or inadequate grounding. In addition, surge protection will be ineffective if it doesn't have a proper path for high-frequency currents. Improper wire size or type and painted surfaces. For example, 60 Hz currents will generally penetrate painted surfaces during fault conditions, but oftentimes higher frequency currents may or may not be adequate to provide low impedance path for stray or unwanted currents from electronic components or induced currents from PWM inverters. In most cases, highly stranded and braided cable or bus bar with the shortest possible length is the most appropriate grounding method for high frequency currents, as it provides significant surface area for the skin effect phenomena of high frequency currents. Circulating currents, ground loops, isolated grounds, and single point grounding. This can be a slippery slope, and oftentimes it's problematic to force a system to have a single point grounding for quote-unquote sensitive equipment. I've seen plenty of situations where ground loops from AV equipment has caused electrical noise and must be eliminated, but there are well-proven methods for dealing with this situation. It's often thought that dirty power grounds should be kept separate from the sensitive equipment grounds, But this is not only dangerous, but risky from a power quality standpoint and potentially damaging to equipment, aside from the fact that it's an NEC violation. We gave an example of a situation where isolated grounds were a problem with a lightning strike and improper grounding in our power quality solutions video. Isolated grounds like you would find on a hospital plug are a different story and can certainly help from a PQ standpoint, but should be installed with care and as intended. The bottom line is that PQ problems related to grounding can be handled, but they should be dealt with like any other power quality problem. Identify the symptom, find the source of the problem, and determine the right solution. But if the problem seems unsolvable, don't just blame it on grounding.
For systems with transfer switches, if separately derived systems are to be joined via a transfer scheme, only one neutral to ground connection must exist. Let me show you how you can accomplish this with a typical power system. So let's just take a quick look at an example system where you would have a transfer switch, and obviously you have your utility and your service panel. Off of your service panel, you'll have your grounding electrode. Your grounding electrode conductor will come up to your neutral bar, and then you'll have a bonding strap between your neutral bar and your equipment grounding bar. You'll have a feeder come off of your panel board and feed the transfer switch. On the other side of that transfer switch, we have a generator. The generator will be connected directly to the transfer switch, obviously through some overcurrent protective devices, and then your transfer switch is going to supply loads. So this is a basic layout of a transfer switch with a generator in a system. Now, sometimes people will drive a ground rod and bond the generator hull or the structure to that ground rod, and that ground rod is supplemental. So it's not required by the National Electrical Code. It is a supplemental type of grounding. A purposeful connection between the neutral, that grounded conductor, and that ground rod system, the grounding system over there on that generator, may occur in the field, either on purpose or by mistake. The important thing to understand is when you make that connection, you've established a separately derived system. So when I have a neutral conductor bonded and grounded in two separately derived systems, remember I have it grounded and bonded in my service panel, I have it grounded and bonded in my generator, I need to make sure that I only have one place where that occurs, and to get that done, I need to switch the neutral in the transfer switch. So that means I would need to have, say for example, a 4-pole transfer switch. If I do that, I put a 4-pole transfer switch in, I switch the neutral, everything is fine. A separately derived system implies that you would have a grounding electrode system and you would bond the neutral, the grounded conductor, in the generator with that system. If you have a separately derived system, the implication is that the transfer switch must switch the neutral with a 4-pole transfer switch. But what if I accidentally bonded the neutral to the ground in the generator and I only have a 3-pole transfer switch? How do I fix it? Do I have to buy a 4-pole transfer switch? Sure, you could. Or you could simply unbond the neutral in the generator. But you must be extremely careful on how you operate a system like this, because the return current for the generator neutral will flow back through the other separately derived system or transformer. This is especially important for the electrical workers who will be servicing the equipment.